Okay, in this lecture we're going to cover the next part of our section 11.8 material on the derivatives of logarithmic functions. And the most frequently used logarithmic function is called the natural logarithm, or the logarithm which has a base of e, that is the inverse of the base e or natural exponential function. So let's start by stating the derivative of that natural logarithmic function as follows. So if we have the function f of x is the natural log of x, then the derivative f prime is given by 1 over x. Or if we make this a little more interesting, if we say have a function of the form f of x is the natural log of g of x, that is the natural log of a function of x, then using the chain rule, the derivative would be 1 over the function g of x, but then we have to multiply by the derivative of that inner function, that is g prime. So that would leave us with the following. The derivative of the natural log of a function would be the quotient, where our numerator is the derivative of that inner function, and then we're dividing by that function itself. All right. Or in English here, the derivative of the natural logarithm of a function is found by taking the derivative of that function divided by that function itself. So let's look at some examples making use of the derivative of this logarithmic function. So in part A, we have y equals the natural log of 8x cubed minus 3x. That is the natural log of a function. So if we use our new rule for differentiating logarithmic functions, we would have a derivative given by the derivative of the inner function. So in this case, the derivative of 8x cubed would be 24x squared, minus the derivative of 3x is 3, and then we divide by the inner function, which was 8x cubed minus 3x. So we have the following for that derivative. Now in part B, we have y is x squared times the natural log of 5x cubed. So since we now have a product of functions and the logarithm of a function, we have to make use of the product and chain rules. So here by using both the product and chain rules, we would have a derivative y prime of, well, we first differentiate the first function, x squared, in our product, which would give us 2x, and then we multiply by the second function in our product, which was the natural log of 5x cubed. And then we add the first function, which was x squared, times the derivative of the second function. Now the derivative of the natural log of a function gives us a ratio where our numerator is the derivative of that inner function. In this case, 5x cubed would give us a derivative of 15x squared. And then we divide by that inner function, 5x cubed. Now we can simplify this a bit in the following way. We have our 2x times the natural log of 5x cubed. And then this second part that we're adding, let's see how we can simplify. So we have a 15 divided by 5, which will give us a constant of 3. And then we have an x squared times x squared, which would give us x to the 4th power, but we're then dividing by x cubed. So x to the 4th divided by x cubed, if we cancel 3 powers of x, we're left with x to the 1st. So this would be the simplified expression for our derivative. Now in part C, we have y is the natural log of x divided by 2 times x. So to differentiate, we would make use of the quotient rule. So here, by using the quotient rule, our derivative, y prime, is found by first differentiating the numerator. Now the derivative of natural log of x, we stated in our theorem, was 1 over x. And then we multiply by the denominator, which was 2x. Then we subtract the numerator, which was the natural log of x, times the derivative of the denominator. So the derivative of 2x would just be 2, and then the entire thing is divided by our denominator, which was 2x quantity squared. So let's simplify a little bit. So starting with the first term in our numerator, if we have 2x and then we're dividing by x or multiplying by 1 over x, we're left with just a constant 2. Minus, for the second part of our numerator, we're multiplying 2 and the natural log of x, so we have 2 log x over squaring our 2x in the denominator. We would have 2 squared is 4 times x squared. Or if I want, I could factor out a 2 from each term in the numerator, and I'm left with 1 minus the natural log of x over 4x squared. And then I can cancel or simplify the 2 divided by 4 as 1/2. So this leaves me with 1 natural log of x divided by 2 times x squared. So this would be my derivative in simplified form. All right, so let's look at some others. In these next examples, we're going to make use of properties of the logarithm to simplify our differentiation process. So in some examples, we'll have the natural log of some complex function. And if we were to evaluate the derivative directly, it would be a pretty tedious process. But if we use properties of logarithms, we can simplify the process of finding the derivatives of these sorts of functions. Now, the properties that we're going to make use of are the following. So you can recall these from your pre-calculus class or business math class. Now, the first property is that the log of a sum, the log of a product, say x times y, is equal to the sum of the logarithms of those factors. So that is the natural log of x times y is the same as the log of x plus the log of y. So logarithms turn products into addition. Similarly, in part 2, if we have the natural log of a quotient, say x divided by y, that's the same as the difference, natural log of x minus natural log of y. So logarithms turn division into subtraction. And the last property, which we've already made use of in the last lecture when we were looking at the proof of the derivative for a to the x, is this property number 3, which says that the natural log of x raised to some power n is the same as n times the natural log of x. So that is, you can take exponents out in front of logarithms, and it's the same value. So let's look at how we could use these properties of logarithms to simplify the process of finding the derivative for certain functions. So in this next one, we are asked for the derivative in part A of the natural log of the square root of x minus 8. So to evaluate that directly, we would have to make use of the chain rule a couple of times. But if we think about rewriting this function first, we'll recall that the square root of an expression is the same as taking that expression to the 1/2 power. And now, if I have the natural log of some quantity raised to a power, using my property number 3 for logarithms, this exponent, 1/2, I can pull out in front of my logarithm, and I've got half the natural log of x minus 8. And this function is now much easier to evaluate. I only need to use the chain rule once. So making use of the chain rule, our derivative, y prime, would be half of, well, to get the derivative of the natural log of a function, we take the derivative of that function. So here the derivative of x minus 8 is 1. And then we divide by that function itself, which was x minus 8. Or simplifying, multiplying these fractions, we have 1 divided by 2 times x minus 8, or 2x minus 16. So let's look at another one. In part B, we have y is the natural log of a quotient of 2 polynomials. So to evaluate our derivative directly, we would have to use the chain rule and the quotient rule. However, if we recall that the logarithm of a quotient is the same as the difference of 2 logarithms, we could rewrite this as the natural log of 7x minus 1 minus the natural log of 12x plus 5. And now to differentiate this function, we could differentiate each of these logarithms individually using the chain rule and take the difference of these values. So y prime would be, well, we'd first differentiate the natural log of 7x minus 1. So we take the derivative of our inner function, which is 7, and then we divide by that inner function itself, which was 7x minus 1. Then we're subtracting the derivative of natural log of 12x plus 5. So the derivative of that inner function is 12, and then we divide by the function itself, 12x plus 5. So this is much easier than trying to make use of the chain rule and the quotient rule together. So let's look at another one. In part C, we have y is the natural log of a quotient of products of polynomials, some of which are being raised to powers. Now to evaluate that derivative directly without using properties of logarithms, we'd have to use the chain rule, the quotient rule, and the product rule. And then within those steps, we'd have to use the chain rule to differentiate some of these individual factors. So this becomes extremely tedious to do directly. However, if we recall that the natural log of a quotient is the difference of the logarithms, we can write this as the natural log of x squared plus x plus 1 times 4x minus 3 to the 5th minus the natural log of our denominator, which was x to the 5th plus 8x squared all to the 4th. And now, in this first factor, we have the natural log of a product of 2 terms. And recall, the log of a product is equal to the sum of the logarithms. So we could write this first term as the natural log of x squared plus x plus 1, and then plus the natural log of the second factor, which was 4x minus 3 to the 5th. And on the end, we still have this negative natural log of x to the 5th plus 8x squared all to the fourth. So now, in my last two terms, I have the natural log of some polynomial which is being raised to a power. So as we did in part A, these powers I can bring out in front of these logarithms, and I have my initial term, natural log of x squared plus x plus 1, plus 5 times the natural log of 4x minus 3, minus 4 times the natural log of x to the fifth plus 8x squared. And now that I've decomposed my function into a sum or difference of a few terms, I can differentiate each of these expressions individually using the sum difference rule and making use of the chain rule to differentiate each logarithmic term. So the derivative of my first logarithm, so we're finding y prime now, would be the derivative of this inner function, which is 2x plus 1, divided by the inner function, x squared plus x plus 1. Then we're adding 5 times the derivative of natural log of 4x minus 3 is found by taking the derivative of that inner function, so 4, divided by the inner function itself. And then I have a minus 4 times the derivative of this last logarithm would be found by taking the derivative of the inner function, so 5x to the fourth plus 16x to the first, divided by the inner function, which was x to the fifth plus 8x squared. And simplifying just a little bit to finish out the problem, well, I have a 2x plus 1 divided by x squared plus x plus 1, plus for my second term, the 5 times 4 will give me a numerator of 20, which I'm then dividing by 4x minus 3. And then we have a minus if I distribute this constant 4 through to the numerator. I have a 20x to the fourth plus 64x over x to the fifth plus 8x squared. All right. So we have the following expression for our derivative. And it was of course, much easier to find our derivative in this way instead of trying to use the direct approach where we've got to use the chain rule, product rule, quotient rule, and chain rule multiple times throughout. So let's look at the next part of our section where we'll consider the derivative of a more general logarithmic function. So just like we were considering for exponential functions, well, not every exponential has a base of e. We had exponentials of the form a to the x power. So similarly, we do not have every logarithm with a base of e. So recall here that the natural logarithm of x is actually the logarithm base e of x. It's just a different notation. So in general, if we're considering a logarithmic function with an arbitrary base a, then the derivative of that function is given by 1 over x times the natural log of that base, a. So that is 1 over the natural log of a times x. Or extending this to a little more general case, if we have f of x is the logarithm base a of a function, g of x, then by making use of the chain rule, our derivative would be found by taking 1 over the natural log of the base a times the function g of x, which is our inner function. But using the chain rule, we then have to multiply by the derivative of that inner function, which gives us a g prime of x. So this is very similar to what we saw for the natural logarithm. The only difference is if we have a base a logarithm, we have to multiply our denominator by the natural log of the base. So let's see why we have to do this. So if we're considering a general exponential function, say f of x is log base a of x, we can write this in the following way using a change of base formula for logarithms, which says that log base a of x is equivalent to the natural log of x divided by the natural log of the base. So any logarithm can be rewritten in terms of the natural logarithm that we're a little more familiar with. Or we can think about this as 1 over the constant natural log of a times log x on the end. So differentiating this, f prime of x, we have 1 over the natural log of a, which was our constant, and then we're multiplying by the derivative of the natural log of x, which is simply 1 over x. So taking the product, we have 1 over the natural log of a times x, which is what we wanted to show. So let's look at some examples differentiating these general logarithmic functions. So in part A, we have y is written as log of x. Now recall that this notation is representing the common logarithm, which is log base 10. So this is called the common logarithm. So instead of writing log base 10, you'll sometimes see texts or calculators use just log of x, but that's just notation for log base 10. So using our new theorem, the derivative of the common log of x would be 1 over the natural log of the base, which was 10 here, times x. So let's look at another one. In part B, we have y is log of x squared plus 1. So again, this really represents log base 10 of x squared plus 1. So differentiating using the chain rule, since we have a composite function, our derivative of the outer function would be 1 over the natural log of the base, which was 10, times the inner function, x squared plus 1. But then the chain rule says we have to multiply by the derivative of the inner function. So the derivative of x squared plus 1 is 2x, or writing this as a single fraction, we have 2x divided by the natural log of 10 times x squared plus 1. All right. And in part C, we have y is log base 4 of 6x to the 4th minus 2x. So again, using the chain rule, the derivative of the log base 4 of a function is 1 over the natural log of the base, which was 4, times the inner function, 6x to the 4th minus 2x. And then we have to multiply by the derivative of that inner function. So the derivative of this innermost function is 24x cubed minus 2. Or writing this as a single fraction, we have 24x cubed minus 2 all over the natural log of 4 times 6x to the 4th minus 2x. All right.